Let's get into it. Number 10. The continent-sized acid wall. For decades, we have looked at Venus and pictured a smooth, featureless yellow sphere. That uniform blanket of clouds hid the violence happening underneath. If you sent a probe into the upper atmosphere today, it would not find a gentle, swirling fog. It would crash violently into a continent-sized wall of sulfuric acid. The Japanese Akatsuki orbiter recently spotted this massive front moving slowly across the planet. To understand the scale of this structure, you have to throw away everything you know about Earth weather. This is driven by a planetary-scale hydraulic jump. In fluid dynamics, a hydraulic jump happens when a fast-flowing fluid suddenly encounters a slower region. The energy has to go somewhere. The fluid violently piles up. You see this in the water at the bottom of a dam spillway. Now scale that up to an entire planetary atmosphere. The high-speed Venusian winds slam into slower air masses. A massive atmospheric traffic jam occurs. The only way out is straight up. This forces a violent, continuous updraft. It launches highly concentrated acid vapor from the deep, hotter layers into the freezing upper layers. When it hits the cold, it rapidly condenses into a choking, dense fog bank. This fog bank is thousands of miles long. For any explorer we send down there, this is not just an area of bad weather. It is a giant atmospheric machine. It actively scoops up corrosive liquid from the depths. It dumps it directly onto whatever altitude mission planners mistakenly thought was safe. Space agencies plan mission profiles down to the millimeter. They calculate thermal loads. They measure wind shear tolerances. They assume certain altitudes have predictable acidity levels. This hydraulic jump ruins those assumptions. It proves the atmosphere is actively fighting any attempt to explore it. A balloon probe floating gracefully at 50 kilometers up could suddenly be caught in this vertical river. It would be thrown upward into freezing temperatures while being coated in concentrated acid. The structural stress would tear the balloon material apart in minutes. If you were designing a billion-dollar balloon mission to study Venus, what altitude would you target? How would you avoid an updraft that can throw acid miles into the sky? Let me know your engineering strategy in the comments below. Number 9. The iron-rich ultraviolet absorbers. If you look at the clouds of Venus through an ultraviolet filter, you will see stubborn, dark streaks that absolutely refuse to fade. For nearly a century, nobody knew what they were. Some of the most brilliant minds in astronomy, including Carl Sagan, speculated about them. They thought these dark patches might be floating colonies of airborne microbes. They proposed these microbes were soaking up ultraviolet light for energy. It was a beautiful theory. Recently, however, scientists locked themselves in a laboratory. They painstakingly recreated the extreme Venusian atmospheric conditions. They finally found the true culprit. It is far more dangerous than any bacteria. The dark spots are actually tiny iron-rich minerals. They form directly inside the suspended acid droplets. Meteor dust and deep volcanic ash supply the raw iron. The extreme acid environment forces that iron to crystallize. It forms specific minerals known as rhomboklase and acid ferric sulfate. This means the clouds of Venus are not just made of liquid droplets. They are filled with floating, solid mineral grit. These minerals absorb ultraviolet light perfectly. They create the dark streaks we see from telescopes on Earth. This poses a catastrophic threat to spacecraft. If an exploratory probe attempts to open a sensitive sampling vent to analyze the atmosphere, its delicate instruments will not just get wet. They will get clogged with jagged iron dust. This mineral grit darkens the sky. It completely ruins precise chemical readings. Optical sensors rely on perfectly clear lenses to measure light spectrums. A coating of iron sulfate grit will scratch the glass. It will blind the sensors permanently. We used to look at those dark patches and hope for signs of life. Now we know they are a hostile mineral abrasive. We are sending machines into a planetary scale grinding wheel. What material would you use to coat a sensitive camera lens? How would you design it to survive a combination of liquid superacid and solid iron grit? Drop your material science solutions below. Number 8. The stability of biological building blocks. We've always assumed that a single drop of 98% sulfuric acid destroys complex biology on contact. That is a fundamental assumption in organic chemistry. It guides how we search for life in the universe. But in 2023, a research team decided to actually test that long-held belief. They took the core molecular building blocks of life on Earth. They dropped them directly into a vat of 98% concentrated sulfuric acid. They kept the acid at the exact temperatures found in the Venusian cloud layers. They fully expected the molecules to dissolve instantly into a useless sludge. Instead, the results shocked the entire astrobiology community. The fundamental letters of DNA remained perfectly stable for weeks. This included adenine, cytosine, guanine, thymine, and uracil. 19 biogenic amino acids also survived without any degradation. The acid did not destroy them. It hosted them. The molecules were comfortable in an environment that effortlessly eats through solid steel. This discovery completely shatters the oldest rule in space exploration. For 50 years, we have assumed that finding life means finding liquid water. We tell the public to follow the water. But the harsh clouds of Venus possess the exact chemical stability necessary to support a completely alien biochemistry. We might be spending billions of dollars looking for water-based cells on Mars or Europa. Meanwhile, we are completely ignoring a thriving microbial ecosystem right next door. This ecosystem could use sulfuric acid as its primary biological solvent. Water is a great solvent because of its polarity. Sulfuric acid also possesses intense polar properties. It can fold proteins. It can support complex molecular structures. It just does it at a terrifying level of acidity. If you think biological life can evolve and exist without a single drop of water, I want to hear your theory. Explain how you think an acid-based organism might function down in the comments. Number 7. Stardust seeds and micrometeor haze. Venus is constantly bombarded by debris from the inner solar system. Thousands of tons of meteors burn up in the Venusian sky every single year. When they ablate in the upper atmosphere, they leave behind an ultra-fine mineral smoke. This smoke is incredibly rich in iron and magnesium. Gravity slowly and relentlessly pulls these microscopic particles downward. As this smoke sinks through the thick cloud deck, the extreme environment alters it. The intense heat causes the sulfuric acid surrounding them to slowly evaporate. What is left behind is a hard, metal-rich seed. Over time, these seeds undergo a process called coagulation. They clump together. They form a permanent, incredibly thick haze layer just beneath the main cloud deck. This has terrifying implications for future planetary exploration. Any spacecraft falling through the Venusian sky is not just gliding through a toxic, gaseous fog. It is flying directly through a planetary sandblasting chamber. An explorer probe is dealing with a sky full of tiny iron bullets. These micrometeoric particles will aggressively pit optical lenses. They will scratch thermal heat shields. They will instantly contaminate every single atmospheric sample the probe tries to collect. The very stardust that makes up the universe is weaponized by the Venusian atmosphere. This haze layer acts like a physical barrier. It reflects light and blocks our view of the surface. We have not sent a dedicated heavy lander to the surface of Venus since the Soviet Venera missions in the 1980s. Those heavy titanium spheres barely survived the descent through this abrasive grit. Their lenses required thick protective quartz caps that popped off only after landing. Tell me in the comments if you remember seeing those grainy, yellow, distorted Venera photos on the evening news when you were younger. Number 6. The thunderstorm forges. The clouds of Venus are not passive layers of gas. They are incredibly electrically active, as the mineral dust and heavy acid droplets collide violently in the high-speed global winds. They build up massive electrostatic charges. The entire atmosphere functions like a global static generator. Eventually, those massive charges break down. This results in massive lightning strikes. But this lightning does not just create a flash of light in the dark. The extreme thermal energy of a lightning bolt rips atmospheric molecules completely apart. A plasma channel forms. It breaks apart carbon dioxide and sulfur dioxide instantly. In a fraction of a second, the hot arc chemistry takes oxidized phosphorus. It violently forces it into a rare, reduced gas called phosphine. This is a massive problem for scientists looking for extraterrestrial life. Phosphine is normally produced by living, anaerobic microbes on Earth. It is considered a gold standard biosignature. When telescopes recently detected trace amounts of phosphine on Venus, the world erupted. Headlines claimed we had found alien life. But we now realize the truth is much more mechanical. A single massive thunderstorm on Venus can manufacture a cloud of gas that looks exactly like a biological signature. The lightning acts as an industrial forge. It creates the illusion of biology out of dead chemistry. We might report a monumental discovery of life. In reality, we are simply looking at the chemical exhaust of a very angry electrically charged storm. This complicates every future mission. If our highly advanced sensors cannot tell the difference between a lightning strike and a living organism, how will we ever be certain we have found life? Share your thoughts on this detection problem below. How would you design a sensor to tell the difference? Number 5. Ammonia's microscopic lifeboats. To make the search for life even more confusing, scientists recently detected tantalizing hints of ammonia. This ammonia was floating within the middle cloud layers. This detection is incredibly strange. It breaks our current atmospheric models completely. Ammonia is a basic compound. It should be destroyed almost instantly in a sky completely soaked in concentrated acid. The reaction between a base and a superacid is violent and immediate, but if a tiny amount of ammonia somehow arrives from deep volcanic vents, a strange thing happens. It immediately dissolves into the acid droplet it lands in. When it does, it chemically neutralizes the acid. The surrounding acidity weakens significantly. The pH level rises toward neutral. For a brief, highly unstable window of time, a microscopic pocket of friendly chemistry appears. This pocket exists inside the lethal cloud. These neutralized droplets act like tiny temporary lifeboats. Fragile organic molecules could survive inside them. They could replicate and thrive before the overwhelming acid eventually reclaims the droplet. If life does exist in the Venusian atmosphere, it might literally be hopping from one microscopic lifeboat to the next. It would be in a constant, desperate race to stay ahead of the acidification process. This creates a fascinating scenario for mission planners. A probe might sample 1 million dead, highly acidic droplets. It will find absolutely nothing. Then it might accidentally hit one single neutralized droplet. That specific droplet might contain complex, stable organic chemistry. The chances of intercepting the exact right droplet are statistically terrifying. Do you think these temporary lifeboats are stable enough to allow complex evolution to happen over millions of years? Drop your hypothesis in the comments. Let me know if you think biology can win a permanent war against chemistry. Number 4. Mode 3 particles. For decades, atmospheric models assumed that all the particles in the Venusian clouds were simple, spherical droplets of liquid. We built our instruments based on that assumption. We designed our aerodynamic models around it. We now know that assumption is completely wrong. Data from legacy probes shows there is a specific group of particles in the lower clouds. Scientists designated them as Mode 3 particles. These are not round liquid beads at all. They are solid, non-spherical mineral shards. They are roughly the size of earthly bacteria. Imagine trying to fly a drone through a cloud made entirely of microscopic razors. That is what the lower Venusian atmosphere looks like. When these shards coat the surface of a spacecraft, they do not just bounce off. They trap liquid acid against the exposed metal. They accelerate acid corrosion exponentially through a process called abrasive wear. They chew through thin, highly engineered protective coatings in a matter of weeks. The sharp edges of the minerals grind away the passivation layer of the metal. This exposes fresh material to the acid constantly. If a space agency attempts to send a highly sensitive optical lens to photograph the chemistry of the lower clouds, these razors will relentlessly frost the glass. They will scratch the lens so badly that the camera becomes completely useless long before the mission even finishes its primary descent phase. A multi-million-dollar camera will capture nothing but a blurred, gray smear. Which fate do you think is worse for a billion-dollar exploration probe? Being slowly and quietly dissolved by atmospheric acid, or being permanently blinded by a high-speed storm of razor dust? Cast your vote below and explain your reasoning. Number 3. The Terry byproducts of reactive cloud chemistry. Inside these thick clouds, the sulfuric acid acts like a microscopic pressure cooker. The droplets soak up trace gases like carbon monoxide, hydrogen chloride, and sulfur dioxide. They cook these simple gases into incredibly sticky, heavy, complex molecules. If trace amounts of chlorine or fluorine happen to mix into the droplet, the chemistry takes a very dark turn. It produces byproducts like fluorosulfonic acid. This is one of the strongest superacids known to science. It is orders of magnitude more aggressive than plain sulfuric acid. It does not just dissolve metal. It actively disintegrates atomic bonds. Laboratory simulations demonstrate that these complex molecules form in mere minutes under Venusian temperatures. More importantly, they do not act like a simple liquid. They stick to surfaces like an industrial molecular glue. This sticky, terry substance rapidly eats through aerospace-grade aluminum. It causes advanced structural polymers like Teflon and Kapton to craze, crack, and shatter under stress. Spacecraft rely heavily on these polymers for insulation and flexible joints. A perfectly engineered probe built in a sterile, clean room on Earth could have its joints completely dissolved. Its moving parts would be glued shut by a chemical reaction that researchers only managed to fully understand in a laboratory a few months ago. We are planning to send fragile machines into an environment that actively manufactures adhesive superacids. The atmosphere is designed to tear them apart and glue the wreckage together. How would you design a hinge or a moving mechanical part to survive a sticky acid? How do you prevent chemical glue from freezing a gear mechanism? Let me know your mechanical engineering solutions down below. Number 2. The one-way water shredder. For over 50 years, scientists have wondered exactly how Venus lost all of its ancient Earth-like oceans. The planet was once believed to be a twin of Earth. It was likely covered in shallow seas for billions of years. In May of 2024, researchers finally found the exact culprit. It was hiding in the extreme upper atmosphere. It is a positively charged molecule known as the HCO plus ion. This specific ion acts like a one-way shredder for water molecules. Through a process called dissociative recombination, it captures a stray electron. The resulting violent reaction causes the molecule to violently split apart. This splitting acts like a microscopic cannon. It launches the resulting hydrogen atoms straight out into deep space at incredible velocities. They reach escape velocity instantly. And this is happening at twice the rate anyone previously estimated. The planet is quite literally bleeding its very last drops of water out into the void right now as you watch this video. The clouds we see today are nothing more than a permanent, desiccated graveyard. They are the chemical remains of a world that was once completely habitable. Because this ion constantly shreds any remaining water vapor, it guarantees that the clouds will remain a highly concentrated toxic acid forever. The oceans of Venus are never coming back. They were shredded at the molecular level and thrown into the dark. This is a permanent planetary death sentence. It shows how fragile a planetary atmosphere truly is. Do you think Earth might one day suffer the exact same fate? Could we slowly bleed our oceans into space until nothing is left? Tell me your thoughts in the comments. Number 1. Hidden volcanic chemical tsunamis. Just when you think the Venusian sky has settled into a stable, predictable nightmare, the planet changes the rules entirely. Recent reanalysis of legacy radar data proves the surface is not dead. Combined with new thermal emissivity imaging, it proves that the surface is still hiding incredibly active volcanoes. When these massive geological monsters erupt, they punch massive holes straight through the dense cloud deck. They inject millions of tons of sulfur dioxide, heavy water vapor, and metal-rich ash directly into the upper cloud layers. This fresh, violent cocktail completely shifts the acidity of the entire surrounding region. It sparks rapid radical chemistry where absolutely none existed just minutes earlier. A region of the sky that was relatively calm suddenly becomes a boiling cauldron of new acidic reactions. A passing exploratory probe might take a careful reading during one of these events. It might think it discovered a brand new permanent chemical layer of the atmosphere. In reality, it is just driving blindly through the thick temporary smoke of a massive volcanic cough. This creates a data nightmare for scientists on Earth. If we do not design our upcoming missions like Veritas and Envision to actively spot these volcanic plumes from orbit before they descend, we will fail. We will mistake a temporary geological eruption for the steady state of the planet. We will build our atmospheric models on corrupted data. Venus is not a dead, quiet world. It is a highly active, hostile, and constantly shifting machine. The deeper we look at our planetary neighbor, the more terrifying its mechanisms become. It is a planet that actively resists being understood. Which of these 10 terrifying atmospheric discoveries unsettled you the most? Share your answer below. If you respect deep factual science without the hyperbole, make sure you are subscribed.